Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is RET 120 Hydraulics. Today we're going to have a discussion about electrical control of hydraulic systems. Now I know you guys have spent close to a quarter right now learning about some of the coolest things you've ever learned about, namely hydraulic systems. Well, I am about to throw a bucket of ice water upon you. No one is going to hire you for your hydraulic systems ability. People are going to hire you for your ability to troubleshoot and maintain electrically controlled hydraulic systems, because there is no one up in those nacelles in a wind turbine or any other particular remote application sitting there taking a directional control valve manual activation, shifting it back and forth. A computer is doing that all by itself. Okay, so hydraulics, they're the muscle. Electronics, they're the brains. Okay, so hydraulics, they're actually performing the work. The electronics, that's the brains. So basically electronics is telling it when to go ahead and execute. The hydraulics executes it, and it executes it strongly. Okay, so let's go ahead and talk about some basic electrical quantities here and some devices. I am not going to insult your intelligence about going back through all electronics 1, 2, and 3, because you guys should be pretty well versed in all this stuff by now. But I am going to insult your intelligence and talk about a very simple electromechanical device, and that device is the switch. And I'm about to tell you the most important thing you can learn in your entire first year RET program. Please pay attention to what I'm about to discuss here. Okay, this switch is open. When this switch is open, Johnny Electron on this side can't get to this side. He can't get there. So there is no current through an open switch. However, in this configuration that we've just drawn here, there exists a potential rise of 24 volts, whereas this side is hooked to ground. And if I was to take my multimeter and put it in voltage mode, voltage DC mode, V mode like that, what would the voltage be across an open switch? Well, for this particular example, my multimeter should say 24 volts. Okay, this switch is open, no current, yes voltage. Okay, what happens when I close the switch? So now I close the switch. What happens with current? Well, pretty obviously, electrons are capable of completing this circuit. Let's say for the purposes of argument, this is a 24 ohm resistor. So 1 amp of current is flowing from that battery through the switch and through that resistor and to ground. Okay, so closed, yes current. Now voltmeter still in DC voltage mode. I touch terminal across the switch. What is my voltage? Okay, this is the most important concept you can learn in your entire RET career. Okay, in an ideal situation, there is no voltage drop across that switch. So no voltage. Okay? Because if you think about this, let's go straight to Ohm's law. If a perfect switch has resistance of 0 ohms, voltage IR, Ohm's law, 1 amp of current times 0 resistance is 0 volts. Okay? Where does the voltage drop occur? It occurs across the resistor, because this is at 24 volts. This is also at 24 volts. So if this is V1 and this is V2, the voltage drop, V1 minus V2, 24 minus 24, the voltage differential across that switch is 0 volts. Okay? What happens if I take my ammeter, voltmeter, excuse me, and put this lead here? Okay? Now, in effect, what I am reading is the voltage across the resistor, because if this terminal here is at 24 volts and this terminal here is at 0 volts, I'm reading that full 24 volts across that 24 ohm resistor. Okay? So, the most important concept you can possibly learn in your entire entire career here. Okay? This is the most important concept you can possibly learn, the difference between an open switch and a closed switch. Okay? Because this is, believe it or not, the troubleshooting that you are going to be doing. Okay? If there is a violation of any of these two things here, if there's an open switch and there's current, there's something wrong there. You know, there is something wrong with that switch. There's something stuck across the way. If a switch is closed and you see voltage, this is the lizard story. The lizard was stuck in the push button. So here's a lizard. And basically, this thing was not, even though the switch was being pressed, it was not making contact between here and here and here. So the lizard, high resistance lizard, go figure. Now, there was voltage appearing across a closed switch. It's incorrect. Okay. Okay, so enough about that. That is, again, world's most important topic ever. But what I drew, obviously, was a real simple series circuit, where I had a switch and a resistor and a DC voltage source. Not exactly the sexiest thing out there. So it really doesn't do much. Let's go ahead and replace that resistor with something useful, namely a solenoid. Okay? So here's our switch. It's open. This is now solenoid A, which is, oh, by the way, connected to a solenoid operated directional control valve. Solenoid A. What happens here? Press the switch, it closes. Solenoid A is energized, and we go through the straight through position, and our accumulator charges. Pretty neat, huh? What happens when you let go of the switch? Well, it depends. If it's a switch basically with a return on it, it will reopen. And what happens? Solenoid A is not energized, and we go back to our closed position. And we've had a little bit of pressure that's been stored in there. Okay? Simple enough. This is something that you've been using in electronics for quite some time. Just a traditional schematic diagram. There's another way of writing the same schematic that saves a lot of space and really helps you to visualize the control, the logic behind the control. So we had a very simple circuit right there. Let's go ahead and redraw this same circuit in what's known as a ladder, or ladder logic, or control ladder logic, where this rung, this upright is hooked to 24 volts. And this upright is 0 volts. We have a single rung. We have a switch, and we have a solenoid A for directional control valve number 1. The switch, let's call it a push button 1. When it is, so it's a normally open, meaning no current flow through it. What is the voltage across it in its unenergized condition? Well, here's 24 volts. Everything here is hooked to ground. Much easier to conceptualize now, okay? Multimeter comes in. What's he see? He sees 24 volts across that push button switch. Okay, let's say this push button is, you press it, it's going to connect those two, and solenoid A is going to energize. But as soon as you release it, it's going to spring back up to its normally open position. So let's say we put our finger on it now and jam it down. What happens? Now, current can flow through that switch. Where does the 24 volts appear across? It appears across the resistor or the solenoid. Okay? So it's the same circuit, just drawn a little bit differently. So ladder logic, that is what this is, a ladder logic diagram. And let's say, for example, we wanted to install some form of safety. Where we needed both of our hands out of the way. Let's say it's a hydraulic shear, and you want to make sure that this hand that's pushing the button, looks like he's already been working on that shear, he's missing a finger. When he pushes the button, the other hand is not under the hydraulic shear. So what you do sometimes, you actually have two buttons located several feet away from each other, and now you have to simultaneously press both of them for that hydraulic shear to operate. Look at this, PB1, PB2. This is why it's called logic, ladder logic. What this shows is the logical operation and. Push button 1 and push button 2 have to be closed for solenoid A to energize, or solenoid whatever it is to energize. Because if I press push button 1, there is still no current flow because push button 2 is open. If I press just push button 2, there is still no current flow because push button 1 is open. I have to press both push button 1 and push button 2 for current to flow through and energize my solenoid. Okay? That is why it's called logic. So the opposite of an and is an or. So let's say I've got that same hydraulic shear, and I want it to be able to operate it from the left-hand side of this device or the right-hand side of this device. How would I do that? So if an AND was a series connection, think about OR as a parallel connection. Should draw that a little bit better. Push button 2, push button 1. Either one of these could energize solenoid A. Okay? So we'll go ahead and I press this button here. I've energized the circuit. Current is capable of flowing from our plus 24 volt side through push button 1 to energize our solenoid A. Okay, let's say I'm on the right side of the machine. Go ahead and press this button. Current can flow through and energize solenoid A. Let's say I'm on either side, or me and my buddy are on either side. We both simultaneously press that. Either or both of them in combination could energize that machine. So that's what's neat. Ladder logic. And I'm not going to go into all possible occurrences here, but some basics, just the and the or, will help you understand how electrical control systems are basically acting as the brains for the muscle. Okay? So let's go into some basic symbols that we might find in our ladder logic. Pretty obviously, here's our push buttons. That's a push button, and that is normally open. Here's a normally closed. Those are kind of human means of interacting with a system. Push button. There is also devices out there that can be tripped by the machine itself, almost a form of a switch. And that's exactly what it is. It's known as a limit switch. So limit switch, that's a normally open. There's a normally closed. Okay? There's a bunch of different types of limit switches. So if you could think of inside a turbine, inside the pitch here, is a little tag that's dangling off of there. And here's a little device. As the blade pitches around, how do I know that I'm at 0 degrees? How do I know that I'm at 90 degrees? You know, it's using this device as it runs along this way. It's basically going to go ahead and trip itself. It's going to go ahead, if it's a normally open, it's going to close. If it's a normally closed, it's going to go ahead and open. Okay, so that's a limit switch. So these are these push buttons. There's a bunch of different types. Those are kind of human interaction. Limit switches, these are kind of machine interactions. The machine is telling you, hey, I'm at 0. Hey, I'm at 90. There's a bunch of different types of these things. A proximity sensor. Oops. Let me make sure I'm drawing this one correctly. So there's the symbol for a proximity. And what a proximity detector is basically, without physically contacting the device, it's using, basically a ferromagnetic object approaches it, it detects its magnetic field, and it's capable of switching over. So one thing, too, to keep in mind, there's ladder logic symbols for the electrical control diagram, and there are hydraulic schematics. They're describing the same thing, but they're two different schematics. So you're going to see this in the ladder logic symbols, in the ladder logic diagrams. You're going to see that there. But where is this proximity detector for our hydraulic system? You will see the symbol. This is why there was confusion there. That is a proximity detector in a hydraulic schematics. So like like I think it's like a PX1. You're going to see this in the hydraulic symbols. You're going to see this PX1 in the ladder logic. It's the same device, they just got two different symbols because this is hydraulics world, that's the muscle, here's the brain. Okay, but the point of this thing is that's just like a regular limit switch. Okay, it's going to go ahead until it's triggered. It's going to sit there in its normally open configuration. This is our normally open side. Here's our normally closed. When proximity is detected, it will switch over to its opposite state. It will close our normally open side and it'll open our normally closed side. Okay, just like a limit switch. So there's a bunch of different types of limit switches. Think of a pressure sensor or a level sensor. You know, think about, here's a float in a tank that is normally open, and as liquid fills this thing up, it's going to rise until it closes. Okay, so that's kind of a float switch or a level indicator. Similar, very similar type of device that we're going to see in lab. It's a pressure switch. So rather than a ball, it's got this semi-spherical object. That's a pressure switch. So you go ahead and set it to a certain pressure, and pressure will rise and rise and rise. At that pressure, it will go ahead, and in this particular case, it's normally open, it's going to go ahead and close. They're all limit switches. Okay, they're all basically waiting for some interaction, either a non-contact method for a proximity detector, a contact method for a limiting switch, either taking data from the float switch, taking data from the pressure switch. It's all machine inputs. But we got to have a human control of it. Okay, so basically starting something up. Okay, so before we go into some electrical control of hydraulic systems, there's one last. I know this thing is probably hitting you like a ton of bricks right now because you've effectively compartmentalized yourself into electronics and hydraulics and you never thought they would ever touch. Well, everybody's coming to dinner in this lecture here, so we all got to get along. So one last electrical device that we need to talk about, it is super important. It is known as the general purpose relay. So a general purpose relay often takes the unassuming form of a little plastic ice cube, and that's what it's called, is an ice cube relay that plugs into these sockets. And when that relay is damaged, you chuck it and put a new one in. So what's inside a general purpose relay? Well, there's a coil in it. It's an electromechanical device. And that coil has connections to somewhere else in the circuit. And around it are these little connectors. And here's one, and here's two, and this is the control coil for relay 1. This is the contacts CR1A and CR1B, implying that there's two of them. This is contacts A, this is contacts B. And this device just sits there. What this is saying is from terminal 1 to 2, there is a normally closed connection. But from 1 to 3, there's a normally open connection. So what's neat about this is you can use this as either a normally closed switch or a normally open switch, depending on how you wire it up. Same thing over on this side. 4, 5, normally closed. 4, 6, normally open. And the device just sits there. And you're like, what is so special about this thing? Well, check it out. When electrical current flows inside this magnetic coil, it creates a magnetic field, and these devices switch. these contactors switch positions. Our normally closed opens, our normally open closes. Okay? Until that coil is no longer energized and it goes back to its normal state. Pretty neat, huh? Okay, let's go ahead and throw this thing into a ladder logic diagram. Okay, here is our plus 24 volt side. Here's our ground side. Here's a push button. Here's CR1, the control coil for relay 1. Here's push button 1. Here is contactor CR1A. I've taken the normally open side of it. So chances are that's pin 1 and that's pin 3. And here's some motor, or since we're dealing with hydraulic systems, here's some solenoid A. What happens when we press push button 1? Okay, ladder logic diagrams, very similar to a hydraulic schematics. They are shown in their unenergized state. So when we close push button 1, CR1 energizes. What happens to CR1A? Well, it switches its states. It was open, now it closes. Solenoid A energizes. Okay, really neat. What is also cool, I didn't tell you that I had CR1B hooked up in this fashion. And this is, again, is an unenergized state. So when it energizes, it opens. Okay? Now I go ahead, let go of push button 1. What happens? We return to our de-energized state, where CR1A was open and CR1B was closed. And you might ask yourself, well, what is the advantage of this? Well, think of a 3-position solenoid operated directional control valve. Where solenoid A switches it into the straight through position. Solenoid B switches it into the cross through position. And our springs center it. Would you ever want to simultaneously energize solenoid A and solenoid B? What would happen? Well, the immediate wrong answer is that it would stay in the centered position, and that is absolutely true in a world of pointless masses and neglecting air friction, where solenoid A and solenoid B are exactly equal. Well, the deal is, in the real world, which we all live in, one of these guys is always faster, and one of these guys is always stronger than the other. And sometimes you can't tell which is which, okay? So it would potentially shift into an uncontrolled position. This ladder logic control system here we just did is, well, for this particular one, it's always shifted to solenoid B. In its de-energized state, solenoid B is, what does this thing do? Yes. Okay, in our de-energized state, with push button 1 open, solenoid B is activated, and we are in the cross-through position. Push button 1 is pressed down, CR1 energizes, CR1A closes, CR1B opens, thereby de-energizing solenoid B, energizing solenoid A, and going into the straight through position. Okay? What happens when I release push button 1? Again, it returns back to its original state of having solenoid B energized. See, so I just showed the fact that a relay could be used to control several independent branches of a ladder logic circuit, but we've come into a little problem here in the fact that if I press push button 1, I got to kind of keep my finger on it for this thing to work. And we all know that machines aren't exactly working like that. You don't just go ahead and press your computer to turn it on and hold your finger on it the whole time you're using it. You turn it on and you walk away and it does whatever it's supposed to, okay? So we have to come up with a way of establishing the energetic coil, the magnetic field within the CR1 inside the coil and keeping it on until we want to turn it off, okay? This is a pretty critical concept to understand, and this is what's known as a holding circuit, okay? So I'm going to clean this thing up and we're going to draw a holding circuit real quick. Okay, so here is another relay, CR1. It's got 3 sets of contactors associated with it, CR1A, CR1B, CR1C. And what happens when CR1, the coil, is energized, all 3 of these guys simultaneously switch states over to that side, okay? So when the coil is de-energized, they return to their normal configuration. Okay, what we want to do is figure out how to energize coil 1. And then when we're done with the operation, basically turn it off. So we want to have a start button and a stop button. So let's do something like this. Plus 24 volts. Let's have a normally closed button here. I'm going to call that PB1. Let's have a normally open button right here. PB2. And then I'm going to have the coil. Nothing different so far. Here is our solenoid that we want to go ahead and energize here. Solenoid A. I'm going to go ahead and erase this because this is for a different example circuit. Okay, we go ahead and press PB2. This closes, energizes CR1A, CR1, CR1A closes, solenoid A energizes. Does whatever you have to. But again, we're at that same disadvantage where if we let go of PB2, it springs back to its normally open configuration, and CR1 de-energizes, CR1A reopens back up. So how do you make a holding circuit? And how you do that is, if a relay is an electromechanical device where when the coil is energized, it changes the states of its associated contacts, just use one of these other unused contacts in parallel. With our start switch. Watch what happens now. Push button 2 closes, which energizes coil 1, which closes CR1B, which closes CR1A. You let go of the start switch, which hopefully would be able to do. What happens now? There is still a continuous current energizing CR1. Pretty neat, huh? So this is what's known as a holding circuit or a latching circuit. So basically this guy is the holding contact. Okay, it's just something in parallel to the start switch. The immediate question is how the heck do we turn this off? Well, obviously not by pressing the start switch again, but we turn it off by pressing the stop switch, thereby interrupting flow. to the control coil, de-energizes that. These return to their normally open configuration. Pretty neat, huh? Okay, last thing I want to talk about for ladder logic diagram before we go into some simple examples of these things is what's known as mechanical interlock. So mechanical interlock is two switches that are tied together that when this switch is closed, think of this as like a little push bar, it opens this other one. So somebody closes this one, little push bar pushes up on this one, it opens the other one, pops that one open. Okay, so mechanical interlock is just a means of simultaneously switching two switches in different rungs. And sometimes they could even be in the same rung, but typically it's in different rungs in a ladder logic control diagram. And this is probably a better application to what we were talking about earlier, where we don't want to simultaneously energize solenoid A and solenoid B for a 3-position directional control valve. So basically when that limit switch 1 closes, it energizes solenoid B, and the normally closed contact of limit switch 1, because there's a mechanical interlock there, opens up and de-energizes solenoid A. Okay, and there might be some other input logic right here. Okay, so the mechanical interlock is sometimes used to turn off something else when you want to start something else. So making sure that they're not simultaneously starting. Okay. Okay, so the last thing I want to discuss before we actually get into some examples of electrically controlled hydraulic systems is notice that this device here, the general purpose relay, like I said, it's a physical device, and all these things are physically wired up with all those wires connected to physical devices that sometimes could have lizards jammed inside the contacts. They're movable devices and they could wear out and potentially break. And they're all strung together inside some of these maybe not the friendliest ways of making changes to a system. There is ladder logic is slowly but surely being replaced by something called a PLC. So a PLC, if you could think about it, is rather than having these physical devices, these banks of relays inside these boxes, a bunch of physical devices, it's all shrunk down into a computer. And it's a software program that is easily changeable and easily upgradable, that is doing the exact same thing. Okay, when you program in a PLC, you're actually still using ladder. Some versions are particularly some versions of PLC programming are using ladder logic. It's a really neat way of doing it. And let's say you go ahead and made a mistake, or you want to upgrade. What's really neat, rather than adding in the physical device of, let's say, another contactor right here, CR1C or something like that, rather than actually having to do those wirings in there, all you do is put that in the software. It's neat. So you're actually just going ahead and adding another contactor within there. You still actually have to have wires to your sensors and stuff like that, and you still have to have wires to your push buttons, but you can change your ladder logic without actually adding a physical device to it, the actual contactors. So that's a PLC, a programmable PLC, Programmable Logic Controller. And you guys, if you stay around for the second year, you'll actually be doing some programmable logic, programming programmable logic controllers and how to use them inside industrial applications. So again, ladder logic and relays, that was the way they were doing it. PLCs is the way they are doing it now and into the future. Okay, so let's go ahead, and I know this is probably hitting you like a ton of bricks here. Let's just go into a couple simple examples of electrically controlled hydraulic systems, and it's really not that complicated once you know some of the hydraulic backgrounds and some of these very, very, very basic electrical concepts that we've just thus far discussed. Okay, so here is a hydraulic circuit and its electrical control circuit, and let's pretend we're at a job interview and the boss man, your potential boss man, throws these schematics down on the table and he says, tell me what this does. And your immediate response is to jump out the window because this is huge and it's confusing. It's got a bunch of stuff on it. And my response to that is, don't be so quick to jump out the window because you have everything you need to solve what this system does. All you got to do is take it piece by piece. Again, the most complicated system can be broken down into simpler and simpler parts. And looking at each simple component, we're going to figure out exactly what the system does. First off, where is the hydraulic schematic? Where is the electrical control schematic? Obviously, hydraulic schematic on the left, the ladder logic is on the right. Okay, so what does this system do? Let's go ahead, since we're in a hydraulics class, let's just start at the hydraulics. Obviously, there is a pump, a pressure relief valve. It's going to a tandem center directional control valve that is solenoid operated. If solenoid B is energized, it goes through a cross-through connection. If solenoid A is energized, it goes through a straight-through condition. What is going on here at the business end? Well, it looks like there's a cylinder that if it was hooked to the straight-through position, it would just go ahead and extend. This other cylinder here, it's got something in the way. What is this thing that's in the way? Well, it's normally closed, sensing pressure upstream. It's externally drained, and it's got a check valve bypass. It's close to an actuator, i.e. in the hydraulic circuit, and it seems like it's making a decision off the pressure upstream. This to me looks like a sequencing valve. Okay, so as cylinder clamper, it's going to extend willy-nilly. Cylinder press is not going to extend until the clamp has achieved a certain amount of pressure, at which point the press cylinder will extend because our sequence valve will open up. Okay, simple enough thus far. We've done nothing really that is beyond our ability at this point for our hydraulics class. The addition, however, are these two devices here, limit switch 2, limit switch 1. It's making physical contact with a rod end of the press cylinder. Okay, let's see what's going on. Well, LS2, it looks like it is touching it. LS1, if the press cylinder extended, it would touch it. Okay, so let's see what that means inside our ladder logic diagram. Okay, so our ladder logic diagram, it looks like we've got our positive rung right here, our negative rung right here. Looks like we've got a relay coil that's controlling that normally open contact, this normally open contact, and this normally closed contact. Where is limit switch 1? Well, limit switch 1 in the hydraulic diagram is right there, and here it is right here. Limit switch 1 looks to be normally closed. Now, what I'm about to just about to present to you is a Pretty hard concept to understand. Look at the difference between limit switch 1 and limit switch 2. Specifically, this arrow right here. That is part of the schematic because ladder logic symbols, ladder logic diagrams, very similar to hydraulic schematics. They're drawn in their de-energized state. In their de-energized state, the press cylinder is retracted and it's hitting limit switch 2. That arrow means limit switch 2 is normally closed, but it is being held open. Normally closed, held open. That arrow is implying in its unenergized state, i.e. its ready state, it is a normally closed switch, but it is being held open in this particular case by the rod end of the press cylinder. Okay, so I'm just going to draw this thing here. What is that? Well, it's a normally open switch. What is this? It's a normally closed switch being held open. What is this? That is a normally closed switch. What is this? That is a normally open switch being held closed. N-O-H-O. Normally open, held closed. So what that arrow is kind of a modifier to it. So that is a normally open, held closed. Oops, excuse me. Normally open, held closed. Okay? But we are dealing with this circuit right here. I don't want to confuse matters. Okay, so when it's in its natural state, limit switch 2 is being held open. Okay? What are our solenoids? Well, here's solenoid A, here's solenoid B. They are controlling our directional control valve 1, A and B respectively. Finally, how do we start this thing? Well, appropriately enough, the button labeled start. In this particular case, this is push button 1. Well, let's just go ahead and figure out how this machine and what this machine does by pressing the button. Let's just see what happens here. Okay, we press push button 1. And how I'm going to do this, we're going to leave the black. We're going to leave the black, and the black is going to imply that is its normal state, i.e. its de-energized state. What I'm going to do is I'm going to start drawing in red. And what red is going to signify is when push button 1 is pressed. Okay, so push button 1 is pressed. It closes there. Limit switch 1 is closed and is allowing current to flow through. And it energizes CR1. What happens now? All the contacts associated with CR1 go to its opposite state. CR1A closes, CR1B closes, CR1C opens. What happens now? Solenoid A energizes. Oh, by the way, I took my finger off push button 1. What happens? Nothing, because of this holding circuit right here established by one of the unused contacts in CR1. Okay, solenoid A is now energized. What happens? We go to a straight through position. What happens now? Let's go to our hydraulic system. Pressurized flow, enters our clamper, tries to enter our pressing cylinder. It can't. Clamper extends until a certain pressure is reached, at which point the sequence valve says, hey, got enough pressure? Opens up, it starts extending the press cylinder. As soon as it starts extending the press cylinder, what happens? LS2 was normally closed but being held open. It is not being held open anymore, and it closes. I should be drawing this in red. just so we don't get confused. It closes, and I'm drawing it in black as to what it originally was. It closes. Is there a path to energize solenoid B just yet? No, because check out CR1C. It was closed, and now it is opened because CR1 is still energized. So there's still no current going to solenoid B. Okay? The cylinder is now extending. And by the way, what this is implying is, think of like there's some pressing point on the end of that rod. So limit switch 2, it's being held back by that thing in the normally closed held open position. But as soon as this thing starts extending, that switch is up there now, and then it can actually close. Okay, so now it's midway in between. Neither limit switch 1 or 2 are activated. And what happens? Well, it presses through whichever object it's supposed to press through. Let's say it's a piece of wood, it's trying to punch a hole through it. And it travels so far that it hits limit switch 1, which is an appropriate enough time for us to do something with our system. What happens when LS1 changes states? Well, it's normally closed. It opens. What does that do? Well, it interrupts current flow to CR1. And all of these guys change states. And in the case of CR1C, it was a normally closed contact. And because limit switch 2 is closed, current can flow, and we energize solenoid B. Basically, retracting everybody. Because now we're in a cross-connect position. All we do is pressurized flow. It enters our rod ends, and everybody retracts simultaneously until we hit limit switch 2 again. Comes back, hits limit switch 2, holds it open, breaking the current flow from our positive side to our negative side, de-energizing solenoid B, snaps back to our center position, ready to initiate another clamp and press sequence. Pretty cool, huh? So not only did we extend our clamp, then our press because of a sequence valve, what we did was we extended it and retracted it using the brains. Okay, so that is a pretty basic application of electrical control of hydraulic systems. I know, again, this might be hitting you like a ton of bricks because it's the synthesis of a number of things, but look at this. You passed the job interview question because you took things piece by piece and slowly teased how this system works apart, knowing everything you know about hydraulics and just the quick things you've learned about the electrical control of hydraulic systems.